going to try a flash drive now.
Yeah, sorry for the technical glitch.
Yeah. Oh, this could be interesting. We'll make do. We should get going. Okay.
Okay. Sure, let's.
It gave a bunch of font warnings, so this could be fun. All right, so I've been working on Ultra Ethernet for about 3 years now. And we released our 1.0 specification this summer. And so I just want to give you a little bit of retrospective on where the technologies come from, because it's not like we got together 3 years ago and invented a whole bunch of new stuff from whole cloth, right? This is rooted in work that's been done in HPC in the data center for a long time. So let's start by talking about Ethernet. Ethernet always wins is a famous quote by Andy Bechtolsheim, but it's a statement about economics because there is a gigantic economic engine behind Ethernet. Someone said yesterday, we like to employ network administrators. It turns out they all know Ethernet, and what they know is Ethernet, and anything else looks really weird to them. The Ethernet ecosystem is big enough to drive, investments in high-speed SerDes and cables and stuff like that that are hard to sustain outside of Ethernet. Ethernet itself as a technology has never been great for high-performance computing. It's got a lot of barriers as a high-performance network. The link level reliability is not really what you'd want for tightly coupled applications. PFC is kind of clunky as a flow control method. The transports that run over top of Ethernet, well, they're built on process-to-process connections that don't really scale. If you want to stand up 1 million endpoints with, some processes per endpoint, you will very rapidly run out of the Q-pair identifier space when you try to wire up a connection to everybody. Ordering is actually inherent in many of those transports. You heard somebody talk about that earlier today. The actual underlying transport definition has kind of ordering built into how it does its semantics, for example. And then congestion management, well, that's historically been underspecified, to be quite honest. So what happened in AI is they didn't wait around for anybody to do a standard. They went off and built something instead. So you've got people like AWS is very public about SRD. They blast packets all over the place, right? They didn't release that out to the public, they just built it. Google announced their Falcon transport. It works somewhat differently, but those aren't the only two. Lots of people are doing their own variation on the transport, doing clones of Rocky or something like it. You heard about eRocky just before the break. The same kind of concept where it's out building things ahead of the standards because, well, the standards where they are don't work great. Now, what they do all share is that they work inside the same administrative framework that is Ethernet. So they can use those Ethernet network administrators. Everything's IP addressed, for example. They're very dependent on an interoperable switch ecosystem for the most part, right? These customers don't like sole sourcing because Ethernet always wins is an economic statement. So in early 2022, we started having conversations. Slingshot had enhanced Ethernet to work in HPC. We did things like link level reliability. We did credit-based flow control. We did some optimized frame formats. And we started having these conversations where people were saying, hey, AI is booming. It needs communications that look a lot like HPC communications. So can we take those things and standardize them? And we said that was always the goal, was to standardize those enhancements to Ethernet. And I said, hey, in addition to those things, we also do an interesting transport that is more scalable. And wow, you should have, like, it was just dead silence on the phone. They were like, yeah, sure, okay. You can think about it. Well, we formed Ultra Ethernet, and then that's what we did. We went out and we standardized a new transport, and it's the first new transport in 20 years. It's the first one to standardize targeting AI and HPC from the start. We went from a clean sheet of paper to a standard in a little over 2 years. The last 6 months is, every company has to review it, every lawyer has to review it, then they have to polish it up and stuff. It took us a little over 2 years to get a spec done. The Ultra Ethernet Consortium is over 120 member companies now with 1,500 active members. I will say I'm glad they do not all show up to the phone calls because that would be even slower than what it is now. Lots of logos up there. The founding 10 are on top. Well, I won't say that out loud. Okay. How many of you are familiar with the story of Stone Soup? It's an old folk tale. Why do people from South Carolina know this folk tale and nobody else? I don't. Anyways. Okay, so Stone Soup, it's an old folk tale about travelers who show up at a village. They're hungry and they want food, and nobody will give them food. And so they say, well, we'll start making some soup. And they get out their kettle and some water and a stone. And people come up to them and say, what are you making? And they say, we're making stone soup. It's a great delicacy. And this is, the game to get everybody to bring their ingredients along. So let's call that stone Ethernet. So everybody in the story brings along their ingredients as they're asked for some. They're like, well, hey, this stone soup would be a lot better with a few carrots. Now a few potatoes. Now, and as they build along, so we started Ultra Ethernet kind of in a similar way. We took an open source API that was oriented around HPC called libfabric, and we took from Slingshot the connectionless reliability architecture, a semantic layer that supports libfabric, and then from our data center partners and other people who have been working with data center partners, we brought in congestion management solutions that operate over a lossy Ethernet, some scalable shared key encryption solutions that lots of people were actually developing things that looked really similar together, and built together this new modern transport. Okay, so I promised you a little bit of history. So we'll go back to before Ethernet was Ultra and talk about its origins. We'll go back to when this was Ethernet. You can tell it's Ethernet because the ends are coupled together with a T connector. That was how you joined in Ethernets into your coax network. You have to be almost as old as Dan to remember that was Ethernet. So we're going back to the early 1990s when mobile phones looked like this. Social media didn't exist, and supercomputers didn't use Ethernet. So in those days, there was a supercomputer shipped, and somebody said, we've got this great system. It works awesome. It has this really lightly featured operating system, though. So we're going to put a standard operating system on it and use the standard connections that come with that operating system. And so they shipped it. And once you wired up all the connections, there wasn't enough memory left to launch an application, which isn't a very effective supercomputer. And so people got together and they wrote a new operating system with a new networking library that they later dubbed Portals. They called it Portals 0.0, the first incarnation of it, because they recognized that connections were bad. Now, not everybody got that memo. but they recognized a long time ago that connections were bad. Portals evolved over the course of many years. So that was 1991 that they first released something. It was the network API on the ASCII Red supercomputer, after which Intel promptly went out of the supercomputer business. It was the network API on a cluster called cPlant, and then eventually on the Cray XT3 line of computers. What was present in those early systems, and I'm going to admit that in those early days it was easy because the networks just worked. Nobody looks at a modern large-scale network and says, well, that network just works, right? They were reliable. You didn't have to think about it that hard. They just worked. And so they could focus on the semantic layer. And they did things like a connectionless addressing model. They had tagged messaging all the way back in the early 1990s. They had a shared unexpected message buffer. And in fact, very early on, they had the idea that that shared buffer just was linearly consumed by incoming messages. So if you received an 8-byte message, it consumed 8 bytes. And if you received a 4K unexpected message, it consumed 4K bytes. There was none of this. You take a whole receive queue entry, even back in those days. And so then we went to Portals 3.3 on the Cray XT3 with Cray C-star chip. And we learned some things in that time frame. Actually, networks were still mostly reliable if you built them right. Write got harder, so we had to start thinking about reliability in that time frame and how you build a protocol. It was a long way from the CPU to the NIC. The API wasn't designed for that fact because it had earlier instances, the communication coprocessor was just another CPU socket in a dual socket node. And users write bad code. Now, I'm sure that everybody who runs a supercomputer center is shocked to hear that users write bad code. Because back in the day, in the early Portals days, if somebody ran out of unexpected message space, they just crashed the app and they said, that's bad code, go fix that. Well, it turns out if you're a vendor selling the supercomputer, you don't get to give that answer to your customers. Your customers are like, no, really, we want you to fix that. So flow control became a thing we had to think about. So just a minute on connectionless design. So I want to say a bit about what connectionless is. So it means that you don't have user visible connections. It means that the user doesn't have to manage connections. There's no persistent state between a pair of processors that's just there because you happen to maybe be going to communicate with that processor someday. There's no state that scales linearly with the number of nodes. There's no coupling between the semantics and the connections because a lot of APIs today, you have to have that underlying connection if you want the rest of the semantic layer to work. To do connectionless addressing, you point to the node you're going to, you point to the process on that node, you point to the service within that process. That gives you the address space that you're going into. As important as what connectionless is what connectionless is not. It does not have to be unreliable. It does not have to be unordered. It does not have to be something that the user themselves has to build a connection over top of. So connectionless design does not mean unreliable datagram or UDP, because those are solutions that are truly unreliable. You wind up having to build the reliability semantics over top of them. This addressing model actually impacts the packet format, which means it impacts the transport on the wire. On the bottom here, you see a picture pulled from the UEC spec illustrating the way that addressing model works. So we went from the time of Portals 3.3 and we said, well, we learned all these things on the Cray XT3. Let's go fix them. So we refactored the Portals 4 API. And we did a lot of work. A lot of that work was done in co-design with a NIC architecture I was working on at the time. It became BXI eventually. And we'd go back and forth between hardware and architecture team and software team. And we'd say, okay, this doesn't work for the hardware architecture. That's going to be slow. This takes too much space. This makes this structure scale wrong. And so we went through and fixed those things. We added support for PGAS libraries to the API because that was something that didn't exist before. But most of the addressing model kind of stayed as is. We added this idea of a job ID. Well, UEC, we call it a job ID. If we originally called it a user ID, and then somebody said, no, user ID is the wrong construct. We'd already named the API call, so we called it a usage ID instead after that, because this started with a U. But we kept the network identifier, the process identifier, and the index constructs. We kept the reliability model. So one of the things that's different about the way this type of network API works and the way connection-oriented things works is that Portals only fails a given message. If a message doesn't make it through, that message fails, as opposed to tearing down an entire connection. There were 3 families of NICs that have used Portals kind of as their framework. There was BXI and its successors. There was Cassini, which is a slingshot NIC. And in between, there was this OmniPath 2, okay, I labeled it classic because, well, built might have been overstated. We were this close to tape in, this close, when they killed that. And then we got OFI. Now, OFI was an interesting point in this timeline because it was something that abstracted away some of the things that were effectively NIC architecture interface details. And so it allowed a lot larger diversity of implementations underneath while still carrying many of the same concepts in the design. So libfabric was derived from Portals 4. We didn't say that out loud at the time. Politics always get in the way. And then once we had it, though, it made it possible for things like Amazon's EFA, the current OmniPath designs that leverage libfabric, a wide variety of different design points to be built underneath it. So there's our first 30 years of Portals from 1991 to 2021, and we spent a little technical time this morning, so I'll won't leave that up there long enough for you to read it all. All right, so moving from the semantic side to how Ethernet got into this mix, because that was all a story about HPC networking, and none of those design points, except for Cassini, had anything to do with Ethernet. So early on, Cray and Broadcom actually worked together to define something called HPC Ethernet. This defined link level retry, credit-based flow control, optimized frame formats, all of the things that wound up in Slingshot for link enhancements to baseline Ethernet were part of this HPC Ethernet. And this is where, when I say it was always the intent for the link level enhancements to be standardized, well, that's because we worked with somebody to standardize them, and the idea was that that would become a standard. And it kind of didn't go that direction at the end of the day, but a lot of the technology from this showed up in Ultra Ethernet. So adding that to our family tree over here on the right. Next, we'll talk about where Slingshot entered that picture. So when I started doing HPC networking, if you had talked to people and said, I'm going to build your supercomputer using Ethernet, they would have laughed at you and moved on to a different supplier. Okay. So how did we wind up with Ethernet? Well, so if you got the bottom of it, at the end of the day, everybody was going to be using basically the same SerDes. The ecosystem couldn't support the development of a wide range of SerDes technologies anymore. And so everybody was going to be using the same SerDes, the same connectors, the same optics, the same, well, everything. And the problems that were in the Ethernet link, they were relatively easy to fix without having to redo the entire ecosystem. And so that's what we did. We worked with Broadcom, we defined something that fixed the link, and then we built a transport layer over top. We put in a Portals-like semantic layer. We did 2 reliability mechanisms. One looks very much like what's in the reliable ordered datagrams underneath UEC, and one that looks very much like what is the reliable unordered datagrams for idempotent operations that's in UEC. Those 2 protocols were the basis for all of the work we did on the exascale systems. You might wonder why we did ordered, because everything that you heard talked about earlier today and yesterday talked about unordered and the importance of unordered networking. Well, we can do an ordered protocol in Slingshot because the switches take care of the congestion management for us. They will move the ordered flows around other congesting things. They will adaptively route the ordered flow and spit us back out an ordered flow on the other end. So it was safe and easy for us to implement an ordered flow. So you might be wondering, well, okay, that's a great HPC story, but what does that have to do with AI in the data center? Well, that's where congestion control comes into the conversation and where the fonts blew up the slide. Okay. So it is truly amazing how much work there has been done on congestion management over top of lossy Ethernet. I went to try to assemble the heritage of what's in Ultra Ethernet. These are the big picture bullets of where those pieces came from. There are tons of papers behind them. I could not get them all on the screen. I could not get all of the egos associated with them in this building, but that's a different story. So we had ECM-based solutions, delay-only based solutions, receiver-driven solutions. Load balancing emerged that started spreading things over multiple paths, and there were lots and lots of stories around load balancing. Many of these concepts fed into what was eventually built in Ultra Ethernet. And I say fed into because it doesn't look exactly like any of them. There was work yet to be done. So we look at what the Ultra Ethernet congestion control ultimately did. It took ECM marking, it took round trip time, it took packet loss. Optionally, it takes in a packet trimming signal. It uses that information to decide when to taper the rate that it's injecting into the network. I say taper rate, it's a window-based mechanism. It uses it to decide when to reduce the size of the congestion window. But in between, the protocol on the endpoint changes the entropy associated with the packet effectively every packet. And so it sprays the packets all over the network. And then it adapts that spraying based on the feedback it's getting. So it stops using the bad paths and focuses on the good paths that its packets encounter. So the implications of that, you're running in a lossy environment and you're spraying packets everywhere. So in a perfect world, you don't want to have to depend on ordering for anything. And so that's what we did. We took and we built a reliability layer that will accept packets out of order. You track packets with a bit mask beyond what is consecutively received. We have selected acknowledgements associated with that. And then tag matching serves as the glue between the user-facing ordered semantic that you effectively have in Nickel. You send messages between a pair of endpoints. They're expected to get there in order. That's how your buffer is selected. The tag matching feature serves as the glue between that unordered network paradigm and the ordered expectation of the user. And so you tag messages with a sequence, and then no matter how they cross the network, you're able to put those messages back in order at the target and directly deposit them into the user buffer. And so that this takes away any NIC buffering that's required to implement that. So we did go beyond just standardizing stuff that we've all built. A few other things came into the picture. So for security, we wanted the ability to encrypt everything. Everything in the packet, basically, but the Ethernet header and the IP header is encrypted. We do this using a shared key infrastructure, which gives us an actual scalable encryption solution. I don't have time to go into the details of that. We had to build an anti-replay defense mechanism. You'd be surprised how interested people get in the details of security. And they're like, well, these packets may be encrypted, but if you captured one, you could replay it and it could wreak all sorts of havoc. And that is not a trivial thing to solve in the context of a dynamic reliability state stand-up and an out-of-order network. We built a new flow control mechanism. One of the hardest parts that we did in Portals 4 was to solve flow control relative to Portals 3.3. We took another step forward in that and integrated it as part of the spec. And then we released it. So we have now an integrated spec that covers link layer all the way up to software level. It's designed to support things at extreme scale and to scale well out to extreme scale. We've used over 30 years of network research and design in HPC as a driver from that. Everything from the notion of a connectionless API to the connectionless reliability that we demonstrated at exascale with Slingshot, to the congestion management solutions that are coming out of the cloud for running over top of lossy Ethernets using adaptive load balancing with packets sprayed all over the network. We included a scalable encryption solution, and we made optimizations for the next generation. We didn't just stop with where we were. We built something that was going to last for 2 or 3 generations at least. Thank you.
So let's give a big thanks to Pete. We have time for a few questions. Yes, please use the.
I can speak up.
Okay.
So you mentioned security with encryption, right? So when you deploy HPC clusters, they're in like a secure facility with like gated access, controlled access. So what's the context for security that you were talking about? Who are the bad actors that you're protecting against?
Yeah. Ever heard of anybody named Eric Snowden? I mean, this is the reality of the situation. Everybody has secure data centers. Cloud providers have secure data centers, but many of them have had experience with someone who probably works for a foreign state as well as for them, installing something that exfiltrates data. And nobody likes that, right?
Any other questions here or from remote? Yes.
Well, this may be a little bit wild questions. Please forgive my ignorance in this domain. But if your bold statement, not only your statement, but so if the statement "Ethernet always wins" is right, actually I have a personal experience when I worked with in Intel. One of my projects was killed by the Ethernet guys, so I know that fact. But in the same context, then, do you have any plan to support the low